Are you ready to take on the challenge of creating your very own snake game? In this tutorial, I'll be guiding you step by step on how to build your very own snake game using the C++ programming language and the raylib library. We will start with the basics and work our way up to adding some cool features and making the game look more exciting. In order to be able to follow this tutorial, I expect you to have a basic knowledge of the C++ programming language and a development environment for C++ already installed. I am going to work with Visual Studio Code. Lastly, we are going to need the raylib library. I have prepared a detailed video on how to install raylib on your Windows computer and use it with Visual Studio Code. You can watch it here. It will help you set up everything on your Windows computer. If you use a different operating system, you can still follow this tutorial if you have a working C++ setup with the raylib library. So, if you have set up everything and you can compile and run a simple raylib example program, we are ready to go. Today, we will develop a snake game by breaking it down into smaller pieces and solving each one. Here is what we need to do. Let's start at once with step number 1. The first step in building our snake game is to create a blank screen and set up the game loop. Before we start, it is important to understand the structure of a game. Every game consists of two parts: the part where we define our variables and game objects, such as the snake, the food, and the arena, and the game loop, which is responsible for updating the positions of the game objects and checking for collisions. The game loop is like the heartbeat of the game, running repeatedly until the game is closed. In each iteration of the game loop, we will draw the game objects in their new positions and check for collisions, all happening so fast that it appears as a continuous movement. Now let's create a blank screen and the game loop. Let's open the C++ starter template for raylib that I have created with VS Code. You can download this template project by visiting this GitHub repository. If you compile and run this project, it displays a bouncing ball example. In the main.cpp file, remove everything, just leave the return statement. Let's print something to the console to see that our setup is working. Cout, starting the game, end line. If we compile and run the game by pressing F5, at the terminal we can see the message printed. Our setup works. Now let's create a blank screen for our game and the game loop. First of all, we have to create our game window. The game window is like a blank canvas where we can draw our game objects. We need to specify the width and the height of the game window. I am going to use a size of 750 by 750 pixels for now. We will change that later. To create the game window, we will have to call the initWindow function. This function initializes a window and takes three arguments: the width and the height of the window, and the title. For the width and the height, let's enter 750, 750, and for the title of the window, let's enter Retro Snake. Now, every time we create a window, at some point we have to destroy it, and we do so with the close window function. So, let's add the close window function here, before the return statement. We just created a game window, and to draw on it, we use a coordinate system similar to the one taught in high school. Each point on this window has its unique x and y values. The coordinate system used in computer graphics differs from the standard Cartesian coordinate system taught in high school. In computer graphics, the origin of the display is located at the top left corner, with 0, 0 being at the top left. In contrast, the standard Cartesian coordinate system starts from the bottom left corner, with 0, 0 being the origin. In this system, the x-coordinate increases as we move to the right, and the y-coordinate increases as we move up. However, in the top left corner coordinate system used in computer graphics, the x-coordinate increases as we move to the right, and the y coordinate increases as we move down. This means that a point 10,10 will be located 10 units to the right and 10 units down from the origin. We will be using the top left corner coordinate system in our snake game. That's why it is important to understand the differences between the two coordinate systems. The basic setup of the game is ready. Let's now work on the game loop. The game loop consists of 3 parts. Event handling. First, we need to check for any events that occur in the game, such as quitting the game, a key pressed on the keyboard, etc. Updating positions. Next, we update the positions of all the game objects, such as the snake and food, based on the events we detected in step number 1. 3. Drawing objects. Finally, we draw all the game objects in their new positions on the screen. This step uses the raylib graphics functions to render the objects in the display. By following these 3 steps, we can create a dynamic and interactive game that responds to user inputs and updates its state accordingly. We start the game loop with a while loop like this, while, curly brackets. The while loop will run over and over again until we close the game. The first thing we do inside the game loop is to check for any events. Now inside the parentheses we type the condition. Window should close, parentheses, equals false. The window should close function is a very useful function. It checks if the escape key on the keyboard is pressed or if the close icon of the window is pressed, and returns true if that is the case. So, if it returns true, the game loop ends and the window is destroyed. Our game loop needs 2 more functions. First, we need to call the begin drawing function. This function creates a blank canvas so we can draw our game objects on. Next, we need to call the end drawing function, which ends the canvas drawing. Lastly, there is something else we need to do. We have to define how fast the game should run. We do so by calling the setTargetFPS function before the game loop. The setTargetFPS function takes an integer as an argument, and that integer is the number of frames per second that we want. I'm going to use 60 frames per second, so setTargetFPS 60. That's it. If we don't define a frame rate for our game, the computer will try to run the game as fast as it can. So the game speed will depend on the speed of the computer. By defining a frame rate, we make sure that the game runs at the same speed on every computer. For this game, we define that we want to run this while loop and update the display 60 times per second. Now that the game loop is complete, we can run the game for the first time. If we run the game at this point, we won't see anything inside the game window because we haven't drawn anything yet. But the important thing is that we can see the game window with the title and the dimensions we defined, and that we can reliably close the game window by clicking on this X icon here or the escape button on the keyboard. Cool, but the game window is black. Let's make it green. raylib provides several built-in colors, but we will be defining our own colors for this game. In raylib, colors are represented using a struct called color, which contains 4 unsigned byte components: red, green, blue, and alpha. The values for each component range from 0 to 255, where 0 represents the absence of the color and 255 represents the full intensity of the color. For example, to create a red color, you will create a color struct with the following values. Color red is equal to, curly brackets, 255,0,255. The first 3 values represent the red, green, and blue components, respectively, while the 4th value represents the alpha component, or the transparency of the color. In this case, the alpha value is set to 255, which means the color is completely opaque. Our game will have a retro look, so we will be using only 2 colors, green and dark green. We will create 2 color structs to store the values of these colors. So at the beginning of our code, we define the colors like this. Color green is equal to, curly brackets, 173, 204, 96, 255. Color, dark green is equal to 43, 51, 24, 255. Now let's paint the game screen green. Inside the game loop, we call the clear background function. Clear background parenthesis green. So when the clear background function is called, the Windows background is cleared with this green color. This is typically done at the start of each frame of the game loop, so that the previous frame's graphics are wiped clean and the new frame can be drawn without any old artifacts or remnants. If we run the game now, we can see the game window is now green. Beautiful! We just completed a very basic game loop, so we can remove step number 1 from our list. We have made progress. Now let's work on step number 2. We are going to create the first game object. We are going to create a food object. Before we create our game object, let's think about the game logic. To make our lives easier as game developers, we are going to use a technique very common in game development. We are going to create a grid. That is, we are going to divide the game screen in a large number of identical cells. This grid will be invisible in reality. We will just use it to help us with the positioning and the movement of the objects on the display. So if we want to display a food object, we are going to display it inside a cell. Also, the snake object will be a collection of cells, and it will move one cell each time it moves. Let's create the grid now, and we will discuss more about it later on. We are going to create an int variable that will store the size of each cell. Let's call it cell size, and we will set it to 30. Now let's create an int variable for the number of cells for each row and column of the grid. I will call it cell count. We are going to set it to 25. This means that the grid will cover an area of 750 by 750 pixels. That's exactly the resolution of our game screen. So let's remove it from here and let's replace it with this expression: cell size times cell count, cell size times cell count. Cool. Let's now run the game. As you can see, the game window is exactly the same as before: 750 by 750 pixels, which is 25 times 30 pixels. Let's now create the food class, which will create the food object of our game. We type class food, curly brackets, semicolon, public, colon. Now let's think about the attributes the class is going to have. What do we want to know about the food? First of all, we need to know its position on the grid. The obvious way to implement this is to use X and Y attributes for the position on the grid. But there is another way to do it, which will make our lives easier later on. The vector2 struct the raylib library offers. You can think of it as a data structure that contains X and Y attributes, the same attributes that we want for our class. Let's use a vector2 variable to hold the position of the food object. So in our food class we type vector2 position is equal to curly brackets 5, 6. This line of code creates a vector2 struct to hold the position of the food object. The two numbers in the parentheses 5 and 6 are the X and Y coordinates of the food. For example, the food's X coordinate can be accessed by position.x and its Y coordinate by position.y. Keep in mind that these numbers do not represent pixels, but cells. This means that the food's position is at the 6th column and the 7th row in our grid, with the counting starting from 0. Now let's draw the food object on the screen. We are going to create a new method for the food class and we're going to name it draw. Void draw curly brackets. Now, before we draw something, let's talk about how raylib draws simple shapes on the screen. Raylib provides various functions to draw simple shapes on the screen, including rectangles, circles, lines, and polygons. When using any of these functions, you need to specify where on the screen you want the shape to be drawn. For instance, to draw a square, you can use the draw rectangle function. This function takes 5 arguments: the x-coordinate and the y-coordinate of the top left corner of the square, the width and the height of the square, and a color. In our game, we will use a square to represent the food object. Later on, we can replace this square with an image of the food. So inside the draw method of our food object, let's draw a dark green square. Draw rectangle, parenthesis, x, y, w, h, color. We need to know 5 things to draw the food object as a square. The x and y coordinate of its top left corner, its width, its height, and its color. The x is going to be position.x, but since we are using a grid, we have to multiply this by cell size. We do the same thing for the y position, position.y times cell size. Now the width is going to be cell size, and the height is also going to be cell size. The color is going to be dark green. Cool, that's it. Our draw method is ready. Let's use it in our code. First of all, we have to create a food object. So before the game loop, we type food is equal to food, parenthesis. Now all we have to do is to call the draw method of the food object in the main loop. So after this line of code, we type food.draw. If we now run the game, we can see a dark green square on the screen. Beautiful. Our first game object is visible. Great job. Now that we have successfully drawn a square to represent the food object in our game, it's time to take it to the next level by using an actual image. To load an image for the food object, we need to use the loadImage function. This function takes a string argument that represents the path to the image file. I have placed the image for the food object in a folder named graphics inside my game folder. The name of the image is food.png. So in the food class, let's create a constructor to load this image file. But what is a constructor and why do we need it? In object-oriented programming, a constructor is a special method that is used to initialize an object when it is created. It has the same name as the class, and it is automatically called when an instance of the class is created. The constructor is used to set the default values for the attributes of the object or to perform any other necessary setup tasks. In our case, we need a constructor to load an image file when a food object is created. So inside the food class, we type food, parenthesis, curly brackets. That's our constructor. Now we need to tell the constructor what to do. We need to load an image file. So we type image is equal to load image, parenthesis, quotes, graphics, / food.png. This function returns an image. In raylib, an image is a data structure that contains the pixel data of a graphical image. It can be loaded from a file or created programmatically. Once loaded, an image can be used to create a texture, which is a GPU resource that can be used for rendering in raylib. Now that we have loaded the image, we can use it to create a texture using the load texture from image function. This function takes an image as its argument and returns a texture2D struct that can be used for rendering. In raylib, a texture2D is a type of variable that represents an image loaded into graphics memory. The texture2D is an optimized data type for GPU processing, and it is used for faster rendering of images and textures in video games and other real-time graphics applications. So we are going to need a texture2D attribute in our class to hold the texture data. Let's add it here. Texture2D texture. And in the constructor, let's load the texture. Texture is equal to load texture from image, parenthesis, image. Then we can unload the image to free some memory with this line of code. Unload image, parenthesis, image. Our constructor is ready. Let's also create a destructor to unload the texture when the object is destroyed. In C++, a destructor is a special member function that is called when an object is destroyed or goes out of scope. The destructor is responsible for releasing any resources that the object acquired during its lifetime. In our case, we need to unload the texture. So we type tilde food, curly brackets, unload texture, and we pass in the texture. Now that we have a texture loaded in the memory, we can display it on the screen using the drawTexture function. So in the draw method of our class, we replace the drawRectangle function with the drawTexture function. This function needs 4 arguments: a texture, the x-coordinate of its top left corner, the y coordinate of its top left corner, and a tint color. The texture is the texture we loaded. The x coordinate is position.x times cell size. The y coordinate is position.x times cell size, and the color tint is white in capitals. The tint argument is an optional parameter that allows you to apply a color filter to the texture. This means that the texture will be drawn with a color overlay on top of its original colors. The default value of tint is white, which means that no color filtering is applied, which is exactly what we need. Let's test the game once more. Excellent! The food object is now being displayed with an image, making the game more visually appealing. This improvement brings us one step closer to creating a complete and polished game experience. The problem with our code so far is that the food object is going to be created at the same spot every time we run the game. Let's randomize it. In the food class, let's create a new method called generateRandomPos, which will return a vector2 struct with random x and y attributes. Vector2 generate random pos, curly brackets. Instead of a fixed position, we are going to create a random one. Let's create a random value for the x coordinate of the food object. We are going to use the getRandomValue function of the raylib library, which generates a random number in a range. We need a number from 0 to 24 because we have 25 cells on each row of the grid. Float x is equal to getRandomValue parenthesis 0, cell count minus 1. We do the same for the y coordinate of the food object. Float y is equal to getRandomValue 0, cell count minus 1. Now we have to set these values to a vector2 object to return it. Return vector2, curly brackets, x, y. Now in the constructor of the object, all we have to do is to call this method when we set the position of the object. So, position is equal to generateRandomPosition. And now we can remove the fixed vector2 position we were setting here. That's it, our class is ready. Let's test it. If we run the game multiple times, we can see that the food object is created in a different cell each time. Very cool. Our food object is ready. Another step is now complete. Well done. If you made it this far, rest assured, things are progressing more quickly from now on. We had a lot of things to learn so far. Now let's move on to step number 3. Let's create the snake. To represent the snake, we have to draw some of the cells of the screen dark green. We can think of the body of the snake as an array of some cells. For start, let's make the snake 3 cells long. In our code, the snake can be represented as an array of 3 cells, but we won't store the cells in the array, only their coordinates. The easiest way to do it is to use a vector2 struct to store the x and y coordinates of each cell of the snake body, like this. The first item in the array is going to be the head of the snake, and the remaining ones the tail. But let's make our lives easier and learn something new. Instead of an array, we can use a deck to represent the snake. A deck is a data structure that allows you to efficiently add and remove elements from both ends. It stands for double-ended queue. It is similar to a queue, however, a deck allows you to add or remove elements from both the front and the back. A deck is particularly useful in the snake game because it allows us to add and remove elements from both ends of the collection in an efficient manner, a functionality that is essential for the game logic. This will become more apparent as we proceed with this tutorial. So the first element in the deck is going to be the head of the snake, and the remaining ones the tail. Let's write some code to create the snake and draw it on the screen. First of all, let's create a snake class. Class snake, curly brackets, semicolon. As we said, the body of the snake is going to be a deck containing 3 vector2 structs. But before we can use the deck, we have to import it. So at the top of our file, we include it like this. Include deck. Now we can create the snake body as a public attribute. So we type public : deck. and we need to tell it what kind of things it will store. We will store vector2 object, so vector2 body is equal to curly brackets, vector2 curly brackets, comma, vector2 curly brackets, comma, vector2 curly brackets. Now we have to enter some coordinates for the snake body. Let's enter 6,9 for the head and 5,9 and 4,9 for the tail. That's it. Our representation of the snake in code is ready. Now let's draw the snake on the screen. Let's create a draw method which will be responsible for drawing the snake body. Void draw, curly brackets. We need to draw each segment of the snake body. Our snake has 3 segments, 3 cells to be drawn, so we're going to use a for loop to draw them all. Deck offers a size method, which returns the number of elements it contains, so we can loop through all of them like this. For parentheses, int I is equal to 0, I less than body size, I plus plus, curly brackets. Now, as we did before in the foot class, we simply draw a square for each segment. Let's get the x and y coordinates of each segment. Int x is equal to body brackets I dot x and int y is equal to body brackets I dot y. Now we need to draw a square and give it a dark green color. Draw a rectangle. We first enter the x and y coordinates of the square, x times cell size, comma, y times cell size, then the width and the height, cell size, comma, cell size, and lastly the color, dark green. That's it. Now let's create a snake object and call its draw method. Before the game loop we type snake is equal to snake. And in the game loop, after drawing the foot, we type snake.draw. Let's now run the game to see our snake for the first time. Beautiful, the snake is visible. If we look at the code closely though, we can see the compiler is not happy with our for loop here. It warns us that we compare 2 values of different data types. The deck.size method returns an unsigned int and our I variable is an int. Let's fix it. We just type unsigned here and the warning is gone. Let's run the game once more. As you can see, each segment of the snake's body is a square, so the snake appears like a rectangle. Let's make each segment of the snake body a rounded rectangle to be more pleasing to the eye and to be able to see the discrete segments of its body. So in the draw method of the snake class, we change the draw line. Instead of the draw rectangle function, we are going to use the draw rectangle rounded function. The draw rectangle rounded function in raylib is used to draw a rounded rectangle shape on the screen. The function requires a rectangle type as the first parameter, which represents the rectangle that will be drawn. The rectangle type is defined in raylib as a structure that contains 4 properties, x, y, width and height, which represent the position and size of the rectangle. When you pass a rectangle type to the draw rectangle rounded function, the function will use the values of the x, y, width and height properties to determine the position and the size of the rectangle to be drawn. Then we have roundness, the radius of the corners of the rectangle, segments, the numbers of line segments to be used to draw each corner. These parameters affect the smoothness of the corners, with a higher number of segments resulting in smoother corners. And lastly, we have color, the color of the rectangle. Let's enter all the information the function needs. First, let's create a rectangle outside of the function call to keep it cleaner. Rectangle segment is equal to rectangle, curly brackets. We need x, y coordinates and the width and the height. X times cell size, comma, y times cell size, comma, cell size, comma, cell size. Now we pass this struct to the function. Segment, comma, 0,5 for roundness, 6 for segments, and dark green for color. If we now run the game once more, we can see our snake has rounded segments. Cool. If we look at the code, again the compiler is not happy in this line of code here. Each element of the rectangle struct must be a float. That's why the compiler is complaining. Let's make all these values floats. Float x and float y. And float cell size here and here. Let's give it another try. Beautiful. Our snake object is visible and the compiler is happy. Another step is now complete. We can move on to the next step, which is to make our snake move. Let's think about the movement of the snake. The easiest way to approach it is this. As we said, our snake is just a collection of cells, represented as vector2 structs. We can move the snake object by removing the last cell in the collection and adding a new cell to the beginning of the collection. This will allow us to simulate a movement of the snake object across the grid. Let's say we want to move the snake to the right. We remove the last cell from it and we add another one at the beginning, one cell to the right. Our snake moved one cell to the right. Let's say we want to move the snake down. We remove the last cell from it and we add another one at the beginning, one cell to the bottom. The head of the snake moved one cell downwards. Cool, huh? No fancy math required. Just remove the last cell and add another one to the direction of movement. Because we are using vector2 structs to represent the segments of the snake's body, we can easily calculate the coordinates of the segment we are adding. We can perform mathematical operations with vector2 structs. For example, let's take the head of the snake, which is a vector2 struct with an x value of 6 and a y value of 9. We can add another vector to it. For instance, if we add the vector to 1, 0, the resulting vector will be 7, 9, which is like moving the head to the right. If we added the vector to -1, 0, the head will move to the left. In the same way, if we added a vector to 0, -1, the head will move upwards, and if we added a vector to 0, 1, the head will move downwards. Vector2 objects are making our task much easier. Now let's implement this in code. First, let's make the snake move to the right. Then we will implement user input to control its movement. We will add another attribute to the snake class. We need to know the direction in which the snake is moving, and this attribute will be a vector2 struct. So we will add the following line to the snake class. Vector2 direction is equal to curly brackets 1, 0. Now let's create an update method where the position of the snake is going to be updated. Void update, parenthesis, curly bracket. As we said before, moving the snake is just two actions. First, we're going to remove the last segment of the snake's body. Let's do it. Since we are using a deck data structure to represent the snake's body, removing the last item from it is very easy. We just have to call the popBack method. The popBack method of the deck removes the last element from the back of the container. Body.popBack. Now our snake's object body deck has only two elements. We need to add another one to the beginning of the deck. To do this, we'll use the pushFront method of the deck, which adds an element to the front of the collection. Body.pushFront, parenthesis. Now we need to add the head of the snake, but moved in the direction specified by the direction attribute. We can do this by adding the snake's head, body 0, to the direction vector. To add two vectors, we need to use the vector2 add function. To use this function, we have to include the raymath.h file at the top of our file, like this, include raymath.h. So we can now type vector2 add, parenthesis, body 0, direction. This function returns a vector2 struct with the new coordinates for the head of the snake. This will move the snake's head in the direction specified by the direction attribute and add it to the beginning of the snake's body list. Believe it or not, 2 lines of code are needed to move the snake. Now let's call the update method inside the game loop. Before the drawing part of the game loop, let's type snake.update. Now let's run the game to see what happens. As you can see, the snake moves, but it moves too quickly and it disappears from the game window. Let's first address the first problem. The game loop is executed 60 times per second, so the update method of the snake object is also called 60 times per second. This causes the snake to move 60 cells to the right every second, which is why it moves so quickly. Instead of calling the update method of the snake in every execution of the game loop, we need to update it at a slower rate, for example, every 200 milliseconds. This will slow down the snake's movement and make it more visible on the screen. To achieve this, we need to create a function called event-triggered, for example, that will be used to check if a certain amount of time has passed since the last update of the snake. We can use this function to control the update rate of the snake. By setting a time interval of 200 milliseconds, for example, we can ensure that the update method of the snake is only called every 200 milliseconds, which will slow down the snake's movement. First of all, let's create a variable named last update time here at the top of the file and initialize it with 0. Double last update time is equal to 0. The last update time variable is used to keep track of the time at which the last update of the snake occurred. This variable is initialized to 0 when the game starts. Now let's create a new function up here called event-triggered. We want to see if some interval has passed, so we will return a boolean value. So, bool event-triggered, curly brackets. Now, this function is going to take an interval in seconds as an argument, so we type here, double interval. Now, we are going to use the getTime function from raylib to get the current time in seconds since the program started running. Double current time is equal to getTime. We assign this value to a variable called current time. We then compare the difference between the current time and the last update time variables to the specified interval argument. If current time minus last update time greater than or equal to interval, curly brackets. If the difference is greater than or equal to the interval, it means that the interval has passed since the last update. So we update the last update time variable to the current time and return true. Last update time is equal to current time and then return true. Otherwise, we simply return false. Return false. Great, our function is ready. We are going to call this function 60 times per second because we are going to call it inside the game loop. Let's do it. We want to update the snake position every 0.2 seconds. So, if event triggered parenthesis 0.2 curly brackets. If the function event triggered returns true, it means the interval has passed. So we have to update the snake. So, snake.update parenthesis. It is important to remove the call to the snake update method that was previously in the game loop to avoid updating the snake's position more than once per interval. With this setup, let's run the game once more to see if it works. And as you can see, the snake is moving a lot slower. Perfect. Now the snake's movement is visible and the game is more playable. Of course, we can't control the snake yet, so it will disappear from the screen in a few seconds. So let's add keyboard controls to the game. In order to control the snake's movement, we need to detect when the player presses certain keys on the keyboard. To do this, we will be using the isKeyPressed function. It is very easy. We simply add the following code inside the game loop. If isKeyPressed parenthesis key up, this line of code checks if the up arrow key has been pressed. raylib provides a set of constants for different keys on the keyboard, such as key up, key down, key left, key right, etc. Now, since the up arrow key is pressed, we have to move the snake upwards. We can do this by updating the snake's direction attribute to move up, like this. Snake.direction is equal to curly brackets 0, -1. When we set the snake's direction to 0, -1, we are indicating that the snake should move upwards. The vector2 struct represents a 2D vector with x and y components. In this case, we are setting the x component to 0 and the y component to -1. The origin of the game window is located at the top left corner, which means that the y coordinates increase as we move downwards. So in order to move upwards, we need to decrease the y coordinate. That's why we set the y component of the direction vector to -1, which tells the snake to move upwards on the y-axis. Similarly, we can detect if the user has pressed any of the other keys on the keyboard and we change the direction of the snake accordingly. If isKeyPressed parenthesis key down curly brackets snake direction is equal to curly brackets 0, 1. If is key pressed, key left, curly brackets, snake direction is equal to -1, 0. And lastly, if is key pressed, key right, curly brackets, snake.direction is equal to curly brackets 1, 0. Great! We can now control the movement of our snake by using the arrow keys. However, there is an issue with our current code. If the snake is moving to the right and the player presses the left arrow key, the snake will immediately change direction and start moving to the left. To prevent this from happening, we need to add a check to ensure that the snake cannot move in the opposite direction of its current movement. For example, if the snake is currently moving to the right, we should not allow the player to press the left arrow key and change the snake's direction. In the code, we alter the if statements like this. If is key pressed, key up, and snake.direction.y is not equal to 1. Here we check if the y component of the snake direction vector is not equal to 1. If the snake is moving downwards, then the y component of its direction vector will be 1. By checking that it's not equal to 1, we are making sure that the snake is not already moving downwards, and therefore it's safe to change direction to move upwards. We do the same for all the other three if statements. And here, snake.direction.y is not equal to -1, and in this if statement, and snake.direction.x is not equal to 1, and lastly, and snake.direction.x is not equal to -1. Great work! We have successfully implemented the ability for the player to control the movement of the snake. Now, if we run the game again, we can see that the snake moves smoothly and responds to the player's input as desired. This is a significant milestone in the development of our game. Keep up the good work, as we are making steady progress and the remaining tasks should be relatively straightforward to implement. Before moving on to the next step, let's take a moment to organize our code for better management and maintainability. To improve code organization and make it easier to manage in the future, we will create a game class to hold the snake and food objects as well the various methods. The game class will serve as a container for all the elements of our game, such as the snake, the food, and the game state. It will also hold methods that manage the game's logic, such as updating the snake's position, checking for collision, etc. By centralizing all the game's functionality within this class, it will be easier to understand, maintain, and expand upon in the future. Additionally, it will also improve code readability and reduce the risk of bugs by keeping related code together in one place. Overall, creating a game class will greatly improve the organization and structure of our code base, making it easier to work with in the future. So, let's create a new game class. Let's collapse the snake and food classes to be easier to work with, and now, under these two classes we type class game, curly brackets and semicolon. This class will create and hold the snake object and the food object. So, let's create them. Public colon. Snake is equal snake, parenthesis. And food is equal to food. The game class will of course have a draw method in which it will draw all the game objects by calling the draw method of each one of the two objects it holds. So we type void draw, parenthesis, and curly brackets, food.draw and snake.draw. We also need an update method that is going to update the position of the game objects and it will check for collisions. So we type void update, parenthesis, curly brackets. So far we only move the snake, so we only type snake.update. The first version of our game class is ready. Let's create a game object and call its methods. We first delete the food and snake objects here. We don't need them anymore. The game class will create its own food and snake objects. We now create a game class object. game is equal to game. Now inside the game loop we have to make some modifications to the code. Here, instead of snake.update, we need to call the update method of our game class. So we type game.update. Also here, where we check for user input, we need to access the snake object of the game class. So we type game.here and here. We do the same for all the other if statements. It will take me some time. Now the last thing we have to do is to remove these two lines of code where we draw the game objects and just call the draw method of the game class. Game.draw. That's it. If we now run the game once more, we can see it is working like before, but our code is more readable and easier to work with, as we are going to find out later. Let's move on to the next step of the game development, which is to make the snake eat the food. Let's think about this for a moment. When does the snake eat the food? When its head is in the same cell with the food. So the first thing we have to do is to check if the snake's head cell and the food cell are the same for every update of the game. If that happens, the snake will eat the food, and we have to create another food object in another random location. Let's do this. In the game class, let's create another method. Void check collision with food, parentheses, and curly brackets. Now we have to check if the head of the snake is in the same cell with the food. Now we are going to use the vector2 equals function, which returns 1 if two vector2 structs are equal. If, parentheses, vector2 equals, parentheses, snake.body0, comma, that's the head of the snake, and now we need the food position, food.position. Let's print something to see if this works. Cout, eating food, end line. Now we have to call this function in the update method of the game class. Check collision with food. Let's run the game. As you can see, at the console we can see the message eating food each time we collide with the food. Beautiful. Now we have to change the position of the food object each time it collides with the snake. We can call the generate random position of the food object to achieve that. Let's do it. We can delete the cout statement, we don't need it anymore, and let's add the following line. Food.position is equal to food.generate random pos, parentheses. Let's run the code once more. As you can see, now when we eat the food, its position on the screen changes to a random location. But there is a problem. There is a small probability that the new cell position is on top of the snake. We can't allow this to happen. So we have to modify the generate random pos method of the food class to check if the new position exists in a collection of cells. If it is true, it has to generate a new position for the food object. This collection of cells is going to be the snake body deck. Let's name it snake body and pass it in as an argument to the method. Deck vector2 snake body. Now we have to add the following to the method. Vector2 position is equal to curly brackets x, y. Now we have to check if this position exists in the snake body deck. To achieve this, we are going to create a new function. Let's go to the top of our file and create a new function. Bool element in deck, parentheses. This function will return true if a given element is in a given deck, else it will return false. So we're going to pass in two arguments to the functions. The first one is going to be the element we are looking for, vector2 element. And then we need a deck, vector2 deck. Now let's implement it. We have to access every item of the deck and check for the element. For unsigned int I is equal to 0, I less than deck.size, I++. Curly brackets. If vector2 equals, parentheses, deck I, element, return true. Else we return false. Now we can use this function inside the generate random pos method. While, parentheses, element in deck parenthesis, position, comma, snake body, which means that the random position we generated is one of the segments of the snake's body. Then we have to create another random position. We copy this block of code in the while loop like this. But this is not a good programming practice. We have duplicate code here. Instead, we are going to create a method for this block of code. Vector2 generate random cell, parentheses, and curly brackets. Let's paste these two lines of code here and return the random vector2 struct we created. Return vector2 curly brackets x, y. This method returns a random cell position. Now we modify the generate random pos like this. Vector2 position is equal to generate random cell, and while element in deck position is equal to generate random cell, and lastly we have to return that position, return position. The method is now clear and concise. However, since we modified the method arguments, we need to update the method call in all the locations where it is used. In particular, when we first create the food object, we need to pass the snake body as an argument to the constructor here, deck vector2 snake body, and pass it in the call of the generate random pos method here, snake body. In the game class, we need to update the creation of the food object to include the snake's body deck as an argument, snake.body here. And in the check collision with food method, when we call the method to update the food object's position, we also need to pass in the snake's body deck as an argument, snake.body. By updating the food creation and placement method to take into account the snake's body, we can ensure that the food will never spawn on top of the snake. Now, when we test the game again, we can see that it is functioning as intended and the food is placed in a valid location. Another step is now complete. Well done! Now that the snake can successfully locate and consume the food, let's move on to the next step. The snake's growth is an important aspect of the game, and we need to code the behavior that allows the snake to grow by one segment or cell each time it eats food. Before we implement the snake's growth behavior, let's consider how it should work. When the snake eats food, we want it to increase in size by adding an additional segment to its body. It is important to note that this segment should be added to the beginning of the snake's body, as this creates a more natural visual effect. Additionally, when the snake grows, we should not move it at the same time, as this can create an unnatural, jumpy appearance. In summary, when the snake eats food, we will add a new segment to the beginning of its body and not move the snake for that call of the update method. So the update method of the snake class must know if it has to add a segment to the snake or to move the snake. For this, let's create a new attribute to the snake class and call it add segment and set it to false. Bool add segment is equal to false. Now, in the update method, we check the value of this attribute. If add segment equals true, now we have to add another segment to the snake. Else, curly brackets, we move the snake, so we just place the code which is responsible for moving the snake inside the else statement. Now let's write code to add a segment to the snake body. Adding a segment to the snake's body is very easy. We have to push a new element to the body deck from the front. So we are going to use the push front method of the deck. Body.pushFront, parentheses. We need to add another element next to the head of the snake. So to find the position of the next element, we first get the position of the head of the snake, which is body bracket 0. And now we have to add the direction of the movement of the snake. So we are going to use the vector2add function again. Vector2add, parentheses, body bracket 0, direction. That's all we have to do. Now that the snake has increased in size, we have to set the add segment attribute to false. Add segment is equal to false. Now, if we look closely at this method, we can see that we have written the same line of code twice. It is a good idea to remove any duplicate code. So let's rewrite this block of code to avoid this. We're going to move this line of code outside of the if statement and remove it from here. That's it, no more duplicate code. We can move on. At the check collision with food method of the game class, we have to write this line of code. Snake.addSegment is equal to true to notify the snake object that it needs to grow in size. Now we are ready to test our code. As you can see, the snake moves as before, and every time it collides with a food object, it grows in size by one segment. Beautiful. One more step of our game is now complete. Now we have to check if our snake hits the end of the game window. Now this is very easy. All we have to do is to check if the position of the head of the snake is out of the grid at the X and Y axis. Let's create another method for this check in the game class. Void check collision with edges, parentheses, and curly brackets. If snake.body0, that's the head of the snake, a vector to struct. First, let's check if the snake is outside of the grid at the x-axis. So we need to access the x attribute of the head of the snake. .x equals cell count, or snake.body bracket 0 .x equals -1. Here, if the x position of the head of the snake is equal to the number of cells, meaning it has gone past the right edge of the grid, or equal to -1, meaning it has gone past the left edge of the grid, if either of these conditions are true, it means the snake has hit the edge of the grid and a collision has occurred. So we have to end the game. Let's call a game over method. Game over. We haven't created this method yet. We will do so in a minute. Before that, let's check if the snake moved outside of the game window from the top or the bottom of the screen. If snake.body brackets 0.y equals cell count, or snake.body brackets 0.y equals -1, curly brackets, game over. Now let's call this method in the update method of the game class like this. Check collision with edges. It is now time to create the game over method. Void game over, parentheses, curly brackets. At first, let's print a message to see if the collision with the edges of the game window works. Cout, game over, end line. Let's now run the game to see if it works. Okay, the game works, and when we move outside of the game window, a game over message is printed at the console. Cool, our collisions work. Now inside the game over method, we add the behavior we want when the game ends. I'll keep it very simple in this video, but you can add any behavior you want in your version of the game. When the game is over, I will just return the snake to its starting position, move the food object to a new position, and pause the game until the player presses any key on the keyboard. First of all, let's remove this cout statement and let's move the snake to its original position. Let's create a reset method to the snake object to be responsible for that. Let's call this method and implement it at once. Snake.reset. Now, let's implement this reset method in the snake class. Void reset, curly brackets. Body is equal to, curly brackets, vector2, curly brackets 6,9, comma, vector2, curly brackets 5,9, comma, vector2, curly brackets 4,9. And direction is equal to, curly brackets 1,0. We just recreate the original body deck and direction attributes. The new method is ready. Now we have to move the food object to a new position. Again, we are going to call the generate random pose method of the food object. Food. position is equal to food dot generate random pose parenthesis snake dot body. Now we have to pause the game until the player presses any key on the keyboard. For this, we're going to need to add another attribute to the game class. Let's call this attribute running and make it a boolean. Bool running. The running attribute can only have two possible values, true if the game runs and false if the game is stopped. Let's make the attribute true. Now, when the game ends, we have to change the game's running attribute to false. Running is equal to false. Now, we have to make the game stop when the running attribute is false. We can do that easily inside the update method of the game class. We need to execute all this stuff only when the game is running. So we add an if statement. If, parenthesis, running, curly brackets, and now we enter all these calls inside the if statement like this. Let's test the game. The game runs, and when we hit the end of the game window, the game resets and stops running. The game won't restart because we haven't yet defined how the game will restart. That's what we're going to do now. We need to restart the game when the user has pressed any arrow key on the keyboard. The solution to this is very easy. In the game loop, we already check if the arrow keys are pressed. So inside every if statement we have to type game.running equals true to let the game run again. We do the same for the remaining three if statements. Let's test it. As you can see, when I move the snake outside of the game window, the game ends and it waits for a key press. When I press any arrow key on the keyboard, the game restarts. Very cool. The next condition we need to implement is checking for a collision between the snake's head and its tail. If the snake head hits its tail, the game should end. To check for this collision, we need to check if the position of the head is equal to the position of any of the segments in the body. To implement this, we can add another method in the game class called check collision with tail. Let's write code for it. Void check collision with tail, parenthesis, and then curly brackets. Dec vector2 headless body is equal to snake dot body. First, we create a copy of the snake body and we call the copy headless body. Now, from this dec, we want to remove the head, the first element. We can call the pop front method. Headless body dot pop front. Now we just have to check if the head of the original body dec is in the headless body dec. We will use the element in dec function we created earlier once more. If, parenthesis, element in dec, parenthesis, snake dot body 0, comma, headless body. If the snake's head is in the headless body dec, it means that the head has collided with the tail and the game is over. We call the game over method to end the game. Game over. Of course, we also have to call this method in the update method of the game class. Check collision with tail. Let's test the game again to see if the collision with the tail works as expected. As you can see, we have to eat a few objects to increase the snake's size. When the snake is big enough, and when the snake's head collides with its tail, the game ends and waits for a key press to restart. With this, we have implemented all the necessary behavior for our snake game. Congratulations on making it this far and creating a working game. Now let's enhance the appearance of our snake game. We will add a 75 pixel border around the game window and create a rectangle with a dark green border to contain the gameplay area to look like this. To add the border, we will define an offset variable, int offset, with a value of 75 pixels. This offset value will determine the width of the border. Let's adjust the size of the game window to include the frame of 75 pixels on each side. In this line of code, we create the game window. The first two arguments in this call are the width and the height of the game window. We need to increase that by 2 times offset pixels. So we change this line of code like this: 2 times offset plus cell size times cell count, and 2 times offset plus cell size times cell count. We will also create a dark green rectangle in the game loop with no fill and a stroke of 5 pixels to contain the play area. This will create a visually appealing frame around the game window and help distinguish it from the rest of the screen. To draw the dark green rectangle, we will use the drawRectangleLines_x function. The drawRectangleLines_x function is used to draw the outline of a rectangle with customizable thickness and color. It takes several arguments. Draw rectangle lines x, parentheses. We need a rect here, thickness and color. The color is dark green and the border size is 5 pixels. Now let's think about the position and the size of the rectangle. For the rectangle, we want the coordinates of its top left corner, its width and its height. Since we want to have a frame of 75 pixels around the game window, the rect will be drawn with the following coordinates: rectangle, curly brackets, offset -5, offset -5, and width and height, cell size times cell count plus 10, and cell size times cell count plus 10. We subtract 5 pixels from the x and y coordinates because the rectangle has 5 pixel border. That's why we add 10 pixels to the width and the height of it. So to draw the dark green rectangle, the code looks like this. And before we run the game, we have to cast everything inside the rectangle as a float, because the rectangle struct needs floats. Now that we have added the frame, let's see how the game looks. Great! A dark green frame is now visible. Unfortunately, the positions of the snake and the foot are not calculated correctly due to the omission of the offset. Let's fix it now. We need to make changes to the draw methods in both the snake and foot classes. In the snake class, we simply add offset to the x and y coordinates of the rectangle that we are drawing on the screen. Offset plus here and here. We do the same in the foot class in the draw method. Offset plus here and here. We are just adding offset to its x and y coordinates. Let's try the game again. Excellent! Everything is working as intended. Now let's give the game a title, add a score and sounds, and we are done. First, let's draw the game title. We are going to use the default font the raylib library offers. With the default font, displaying text on the screen is very easy. We just have to call the drawText function. Let's call the drawText function inside the game loop, where we draw all the game objects on the screen. drawText, parentheses. Now we need to provide the function the following information: the text we want to draw, the position x and the position y where we want the text to be drawn, the font size and the color. The color is easy, dark green. The font size is also easy. A value around 40 works fine. For the position x and position y for the title, let's put 20 pixels from the top of the screen for the position y, and let's say offset -5 for position x. The text is going to be retro snake. That's it. If we run the game now, we can see that the game title appears. Very cool. Let's now add a score to our game. First, we need to add a score attribute to the game class. So, in the game class, we add int score equals 0. The score will be increased by 1 every time the snake eats a foot object. Let's go to the collision with foot method. Here we have to increase the score by 1. Score plus plus. The last thing we have to do is to reset the score to 0 every time the game ends. So, inside the game over method, we set the score to 0. Score equals 0. Now that we have implemented the score keeping feature, let's display the score on the screen. Again, we are going to use the drawText function to display a text on the screen. So in the game loop, we type drawText, parentheses, Again, we need to provide the function the following information: the text, the position X and the position Y where we want the text to be drawn, the font size and the color. The color is easy, dark green. The font size is again 40. Position X is going to be offset minus 5 pixels, and position Y is going to be offset plus cell size times cell count plus 10. Now we want a text to print for the score. We just want to print the game.score, which is an int number, game.score. So we have to convert it to text. Raylib has a function for that. Text format, parentheses, quotes, %i, game.score. Our function is ready. If we run the game now, we are going to see the score displayed on the screen. Every time the snake eats some food, the score increases, and every time the game ends, the score resets to 0. Now let's implement the final step of the project. Let's add sounds to the game. I have created a new folder named Sounds in my game folder, and in it I have placed two sound files, one named it.mp3 and the other wall.mp3. We want to play a sound every time the snake eats the food and every time it hits the wall. In Raylib, loading and playing a sound file is very easy. First, we have to load the two sound files. So we go to the game class and we are going to create two new attributes for the two sounds. Sound, it sound, and sound, wall sound. Now, let's create a constructor for our game class. Game, parentheses, curly brackets. Now, inside the constructor, we need to call the init audio device function like this. This function initializes the audio device for playing sound in a game. This function sets up the audio system and prepares it for using the game. Now we can load our sounds. Each sound is equal to load sound, parentheses, quotes, sounds / it.mp3. We do the same for the second sound as well. Wall sound is equal to load sound, parentheses, quotes, sounds / wall.mp3. We have loaded the sound files in the memory. Now let's create a destructor for our class to unload them from the memory when the game object is destroyed. Tilde, game, parentheses, curly brackets, unload sound, parentheses, it sound, and unload sound, parentheses, wall sound. Lastly, we have to call the close audio device function to close the audio device. Now, to play the sounds, we just have to call the play sound function. So in our game class, we have to go to the check collision with food method and add the following line: play sound, parentheses, it sound. And in the game over method, we have to add this line of code: play sound, parentheses, wall sound. And with that, our game is complete. Let's test it out. Perfect. The game works, and we can hear the sounds when the snake eats the food or hits the wall. Congratulations on completing this tutorial. If you are looking for more exciting game development challenges with Raylib, you need to check out my tutorial on creating a Pong game. It is an addictive classic that will test your skills and push you to the limit. Thanks for watching. I'll see you next time.